everyone. I'm Sravanti. I'm a PhD student at the Indian Institute of Science, and I'm also a student researcher at Google Research India. Firstly, I'd like to thank Vikash and the organizing team for giving me a chance to present my work here. And it's my pleasure to present my work titled Efficient and Effective Augmentation Strategy for Adversarial Training. This has been accepted at NeurIPS 22 and will be presented next week. Here is a brief outline of my talk. So I'd like to mention that feel free to ask any questions in between. Hopefully, I'll be able to see. If not, you can just unmute and ask the questions. So here is a brief outline. First, I'll present a background on adversarial attacks and defenses, and then move to the motivation of our work. And next, I'll present the proposed method, AJAT or diverse augmentation-based joint adversarial training. And lastly, the experimental results. Deep networks have been successfully used in many applications like autonomous navigation systems, medicine and healthcare systems, and robotics, but they're known to be vulnerable to adversarial attacks. So here we can see that an image on the left, which is a natural image of a hamster, is being predicted correctly by the network with a very high confidence. But when we add adversarial perturbations, that is shown in the center, even a small amount of perturbation, although it doesn't change how the image looks to us, but it actually changes the prediction of the network from hamster to banjo. And the prediction is again with a very high confidence. So these are adversarial attacks, and they're shown to have quite a disastrous impact in real-world applications. For example, here we can see that in a self-driving car system, hackers could actually trick a Tesla into accelerating by 50 miles per hour by just attaching a 2-inch piece of tape here. And in surveillance systems, basically by using some specially designed spectacles, the identity of the person changes. And here we can see that by rotating this image, a benign mole is being predicted as malignant. So these are basically these are quite critical applications, and the motivation to secure these systems has kind of motivated the adversarial defense research. So early adversarial defenses against adversarial attacks, they tried to incorporate some pre-processing methods which were non-differentiable. So these methods such as bit depth reduction and JPEG compression, they could basically prevent the generation of strong white box attacks, and they gave a false sense of robustness. So although there was no additional training cost for these methods, they were later seen to be broken by some of the attacks such as BPDA and EOT. And adversarial training has actually been quite a strong defense for many years now, and we'll see that in some more detail. So for adversarial training, we pass the clean images to a network and compute any classification loss such as the cross-entropy loss. And then we maximize the cross-entropy loss to generate the perturbations, adversarial perturbations, and we restrict them within a bound such as an LP norm bound of radius epsilon shown here. And this could be either L2 or L infinity or anything else. So these attacks are then added to the image to generate adversarial examples. And then we minimize the same classification loss on these adversarial examples. So here, what I show is the basic training formulation of PGD adversarial training, which was one of the earliest successful adversarial defenses, which is considered to be very strong even now. So now let's look at how these attacks are generated. And based on this, again, the defenses can be classified as either single-step or multi-step defenses. Multi-step defenses are more common, and these basically use strong multi-step attacks for training. For example, the PGD adversarial training method that we have just seen earlier, and the trades defense, which I'll talk about in the next slide. And these methods are seen to achieve state-of-the-art robustness, basically because they are able to generate very strong attacks, and hence the defense is also strong. But the problem with these defenses is that they incur a high computational cost, because For example, if 10 steps of attack are used for 10 iterations are used for generating the attack, then the computational cost actually increases by around 11 times. So this has a very high computational cost. And there have been several methods to improve the efficiency of adversarial training. And this involves the use of single-step attacks. So although the computational cost in these methods is lower, but they're also susceptible to gradient masking. So if we look at the loss surface on the left side, this is basically the loss surface of FGSM adversarial training or single-step adversarial training. So here the model basically chooses to obfuscate the loss surface, and it makes it more difficult to generate single-step attacks rather than making the model more robust. So what we expect is actually that the loss surface becomes smoother, which is what we see on the right. But this is what happens, and it gives us a false sense of robustness. Some of the effective adversarial training algorithms, one of them is trades, which has been quite popular over the last few years, and it's one of the best defenses even today. So this optimizes an upper bound of the adversarial risk, and it trades off well between the clean accuracy and robust accuracy. So this is basically the training formulation, which combines the cross entropy loss on clean samples and the KL divergence between the clean and adversarial samples. So firstly, for generation of attack, the KL divergence between the clean and adversarial samples is maximized. And then a combination of these two terms is basically minimized for training. A small modification of this, which is the adversarial weight perturbation, is one of the strongest defenses today. So in this, basically, in addition to the 10 steps of adversarial attack generation in the input space, the authors propose to also maximize loss in the weight space. So the same trades loss is basically maximized in the vicinity of the model which is being optimized, and the overall loss is minimized on this perturbed model. So this actually leads to a flatter loss surface, as we can see here, and it leads to better generalization. So this trick can be applied to any defense. In the proposed algorithm, we actually try to incorporate data augmentations, and we use the trades AWP formulation as our base defense. So before moving to the motivation, if there are any quick questions, I can take them now. Okay, so I'll get started with the motivation of the proposed approach. So prior works have shown that additional data can improve adversarial training. So here in this plot on the left, we see that for CFA10 training, the basic data set size is 50K. And by adding extra training data of say 40K or 100K, the clean accuracy as well as robust accuracy keep increasing up to the point of 500K that we can see here. Similarly, for this was for L infinity threat model. Even for L2 threat model, we see that as we keep increasing the amount of unlabeled additional data, the robust and clean accuracy both improve consistently. So this shows that the sample complexity of adversarial training is higher than standard training, because this trend is not generally seen standard training for CFA10. And it also shows that by increasing the amount of training data in some way, we can actually get better performance in adversarial training. So one of the recent works, they tried to use generated data, like couple of recent works actually tried to use generated data, because it's impractical to assume that we'll have additional unlabeled data which is relevant to the given task. So in this, basically, the training data set is used by a generative model to generate a different data set. And now to get pseudo labels for this generated data set, a standard classifier is trained on the original data set, and it's used to label this generated data set. And now finally, a robust classifier is trained on the pseudo-label generated dataset and also the original training dataset. So using this approach and DDPM-based generative models, a recent work has shown that we can actually get improvements of around 10% in the robust accuracy on CFAR10, which was actually quite a big boost when compared to the progress which was seen in the earlier years. And in fact, we see that if we look at the top defenses on the robust bench leaderboard, then the top 25 defenses, they actually either use extra data or they use synthetic images which are generated from any of the generative models for training. So this actually confirms the fact that additional training data is one of the most important factors in improving both clean and robust accuracy in adversarial training. So naturally, we do expect that even data augmentations should help because we know that adversarial training requires more data. But surprisingly, prior works have shown that data augmentations are not successful with adversarial training. And this is also an experiment which we use to show the same. So if we use, let's say we use auto augment based transformations for training, then although we get an improvement in the robust accuracy when the test set also uses auto augment based transformations, but in the standard test set, without any augmentations, we actually observe a drop in performance. So this shows that augmentations are not successful with adversarial training. So to summarize this section, we know that data augmentation improves standard training performance, and we have seen that additional data improves adversarial robustness. But we also see that data augmentation does not improve adversarial training. So to explain this contrasting behavior, we try to visualize augmentations as a domain generalization problem. And we use a theory from Ben David et al. Here, which tries to upper bound the expected risk on the target distribution using the terms that we see on the right, which we'll be discussing now. So here we actually consider the augmented trained data as the source distribution and the unaugmented test data as the target distribution. So firstly, since we are augmenting the source data set, we are actually increasing the diversity in the source distribution. And we do expect that this should reduce overfitting on the source distribution, and it should result in a lower error on the source data set, which is epsilon s. And from this equation, we see that this forms an upper bound on the epsilon t as well, which is the expected error on the target data. So this helps in basically reducing the target risk as well. A second way in which augmentations impact any kind of training is basically based on the domain shift between the source and target distribution. So let's say the augmentation is very strong, so that there's a huge shift between the source and target distribution. Although the augmentation may actually help in improving the accuracy on the source distribution, it may not actually translate in gains to the target distribution as well. So this can be also seen from this equation here, where this term actually represents the domain shift between the source and target distribution. And a higher value of this term, again, can increase the risk on the target distribution. Lastly, we look at the capacity of the neural network. So here, this constant lambda, it measures the risk of the optimal joint classifier. So basically, if we train on using the source and target data, then what is the risk of this optimal joint classifier? And it's natural to expect that if the capacity of the model is larger, then this risk can be minimized further. Or in other words, if your task is more complex, then it's harder to minimize the accuracy on both source and target distribution. So basically, these are the different ways in which augmentations can actually impact the dynamics of training, whether it's standard training or adversarial training. Now we look at the same thing in view of adversarial training. So how do augmentations impact adversarial training? Firstly, we spoke about reducing overfitting because of better diversity in the source data distribution. And this should naturally improve the performance of adversarial training as well. And we expect that this should increase both the clean accuracy and robust accuracy in adversarial training. Secondly, we spoke about the domain shift between the clean and robust, between the source and target distributions. And we expect that the domain shift is likely to be larger for adversarial images because the augmentations modify images significantly in the input space. And this results in larger changes in adversarial images. So we show some some images in the supplementary section of our paper for reference. And based on this, some of the prior works have also claimed that augmentations which are designed for adversarial training actually need to preserve low-level features of images. So in this paper, they showed that cutout and cut mix based augmentations work very well. And that's because the low-level statistics of images don't change with cutout and cut mix. But whereas if you try to change the brightness or contrast or any such properties like what we see in auto augment, then such augmentations are not able to actually improve the accuracy of adversarial training. Lastly, we look at the capacity of the neural network. So we know that adversarial training is more complex because it tries to also impose a smoothness of the loss surface in addition to minimizing the loss on natural examples. And because of this, we actually need larger model capacities to actually learn both source and target distributions. And this is again observed in the prior works. So it was shown that on WideResNet 7016, which is a very large model capacity, we can actually achieve gains using cut mix based augmentations. So the authors observed a 2.9% higher robust accuracy and 1.2% higher clean accuracy. Whereas the same method, it does not obtain significant gains on smaller architectures like ResNet 18. So they were able to get around 1.7% higher robust accuracy, but there was a drop of 2.5% in the clean accuracy. So this shows that because of the higher complexity of adversarial training, it's more difficult to minimize the loss on the on both the source and target distributions. And this might be one reason why augmentations don't work well with adversarial training. So after this analysis, we basically aim to address the following concerns that prevent the use of data augmentations in adversarial training. Firstly, the large domain shift between augmented and unaugmented adversarial images. Secondly, the larger task complexity of adversarial training, which makes it harder to minimize the joint training loss on both source and target distributions. And lastly, we want to achieve the above without an increase in the computational cost. I'll pause once again for questions before moving to the proposed method.
I think this one question you might be answering in the next section of the talk, but is it like what you said about regarding the model class? Is it also like agnostic to the family of models rather than just the capacity? And again, this is like a very vague way of saying it, but we don't know, like for example, between transformers and CNNs, okay, like these two model families, at least in my experience, behaves very differently. Like when recently we tried to train transformers with adversarial training, we really had to just drop data augmentation altogether.
Okay.
But data augmentation somehow is the key to training transformers with benign training. But that was training, kind of like what you said, turned out to be true, that it was just too hard. Like for a CNN, which actually even a ResNet 18 benefits, maybe not to the best extent, but somewhat. but like a transformer of size as big as a wide ResNet 2810 doesn't benefit from heavy data augmentation, which
Right.
is the motivation behind me asking is about like the dependence on model family, not just the model capacity.
Okay, so at least the analysis so far, it seems to be applying to transformers as well. As like you've mentioned, it's hard to use data augmentations even for adversarial training in transformers as well. So possibly the same explanation can be given for that. But if you're asking about the method as such, whether it can also apply to transformers, I guess it would need some modifications because we use separate batch norm layers for different augmentations, and that cannot be directly applied to transformers. But the same principle, like we can think of how we can actually implement it in transformers.
Yeah, it was just like out of curiosity, but I think yeah, it can be extended.
Sure, yeah, thanks. So if there are no more questions, I'll move to the proposed approach. So this slide basically presents a brief outline of the proposed approach DAJAT, or diverse augmentation-based joint adversarial training. So we propose to use a combination of both simple and complex augmentations during training. So by simple augmentation, we mean the standard augmentation, which is used in adversarial training, which is the pad, crop, and horizontal flip. And by complex augmentations, we mean anything other than this, which is more complex, like the auto augment. So by using both simple and complex augmentations during training, the model can benefit from the diversity of complex augmentations, and it can also specialize on the original data distribution, which is similar to the simple augmentations. So during inference time, we know that the test set is mostly going to be similar to the train set, and it's going to be unaugmented. So we want to also specialize on this distribution, and that's why the use of simple augmentations also helps. Secondly, we propose to use separate batch norm layers for simple and complex augmentations. And this actually helps in offsetting the distribution shift between the two kinds of augmentations. And further, we minimize the JS divergence, the Jensen-Shannon divergence between the softmax outputs of different augmentations. So this actually allows the simple augmentations to guide the learning of the complex ones. And in this approach, basically, we try to use multiple augmentations in a given training batch. So normally in adversarial training, we just have like like a training mini batch of size B for training. But now every image is actually augmented once using simple augmentation and multiple times using complex augmentation. So in the main approach, we actually use one simple augmentations and one simple augmentation and two complex augmentations. So this actually increases the batch size by 3. And this means that even the training complexity would increase by 3, because now if we use, say, a 10-step attack for generating of an adversarial example, then it would be 3 times costlier. But we wanted to limit the training complexity to the same as the previous, the baseline that we use, which is the trades AWP defense. And for this, we try to propose this ascending constraint adversarial training, where we use 2 attack steps instead of 10. And we notice that if we just directly use 2 steps instead of 10 in the trades AWP defense, then it actually impacts both the clean accuracy and robust accuracy. So here we plot the clean accuracy with respect to the training perturbation bound. And it keeps dropping as the perturbation bound increases, because the training becomes very unstable when the number of iterations for the inner maximization reduces. So to stabilize this training, we propose to use an increasing epsilon schedule, a cosine learning rate schedule, and weight space smoothing using the AWP formulation, which I've discussed earlier. So we show that a combination of these actually improves the stability and convergence of training, and we don't need any other methods of, say, changing the training loss or anything else. Just a simple combination of the trades AWP formulation and some of these tricks which are mentioned here can lead to a very stable defense. So we use this in AJAT, and this improves the training efficiency and it makes the overall computation similar to the trades AWP defense. So now we present the AJAT algorithm in more detail. So we take the original image, and here I'm showing two augmentations. So one is the base augmentation, which is pad and crop, and the other is the auto augment. But in the main method, we actually use two of these complex augmentations. So now next we generate a two-step adversarial attack by maximizing the KL divergence on each of these images. Next, we feed the clean image and the perturbed image to the respective networks. So these networks actually share the same weights, but the batch norm layers are different. So we have two sets of batch norm layers, one for the simple augmentations and the other for the complex augmentations. And even if we use several other complex augmentations, we have only two sets of batch norm layers. And then we compute the trades loss on these two sets of outputs. And we also have this JS divergence term between the outputs of different augmentations. So here we have the loss which is used. This is basically the trades loss, the standard trades loss. So first of all, we generate the attack by maximizing the KL divergence, which is typically done in the trades formulation. And further, we compute the trades loss and we perform the AWP step of maximizing loss with respect to the weights, only using the base augmentations because this helps in reducing the computational cost. And now on this perturbed model, theta plus theta tilde, we compute the overall AJAT loss. So the overall AJAT loss, it comprises of the trades loss on each of the individual augmentations and the JS divergence term between all the augmentations. So we now try to see the batch norm layer statistics to understand how AJAT is actually helping. So we check the cosine similarity between the two sets of batch norm layers, one corresponding to the simple augmentations and the other corresponding to complex augmentations. And we see that there's actually some difference in the batch norm layers, which is helping the model to improve its performance. And the difference is larger in the initial layers as we expect. And we have also wanted to show that the improvements that we get because of AJAT, it's basically because we are allowing a different function mapping for the simple and complex augmentations. So we show a simple ablation experiment here where in E2 we basically have separate running statistics and common affine parameters, and in E3 we have common running statistics and split affine parameters. So basically, both of them are able to improve performance over the baseline of having common running stats and common affine parameters by a large amount, by around 3 to 4%. So this shows that we actually just need a separate function mapping between the simple and complex augmentations, and there's nothing special about whether it's implemented using the running statistics or affine parameters. But if we look at the proposed approach, which uses split running stats as well as split affine parameters, then it achieves the best performance amongst all these ablation experiments. We show some more details on the ascending constraint adversarial training here. So AJAT is basically a simple combination of two attack steps, a linearly increasing epsilon schedule, cosine learning rate schedule, and weight space smoothing. And in the paper, we also show theoretically that given a network which is robust within a radius of epsilon, and is also smooth within, it also has sufficient smoothness and weight space within an L2 radius of psi around it, there exists epsilon dash which is higher than epsilon, and a model f theta epsilon dash within the vicinity of the current model, such that the trades loss within epsilon dash is lower at f theta epsilon dash when compared to f theta epsilon. So basically this shows the existence of a solution in the vicinity of the current model, which optimizes the trades loss at a slightly larger perturbation bound beta. So this actually motivates the use of increasing epsilon schedule and also weight space smoothing for better training convergence. We also show this empirically. So we compare fixed epsilon adversarial training and ascending epsilon adversarial training for both ResNet 18 and wide ResNet. So we show the clean and robust accuracy on the last epoch and also the best epoch. And we also show the difference in accuracy between the last and best. So in ResNet 18, the fixed epsilon adversarial training also works reasonably well. There's no instability that we see, but still the proposed approach gets improvements. Whereas at wide ResNet, there's actually quite a lot of difference between the last and best epochs with fixed epsilon adversarial training. And these issues are mitigated using the proposed method. So I'll pause for questions before moving to the results.
I guess we are looking forward to them.
Okay.
Thanks.
Okay, so firstly, we show results on CFAR 10 on both ResNet 18 and wide ResNet architectures. So we compare with, first of all, we compare AJAT with nuclear norm-based adversarial training, which is our work, which was at NeurIPS 21. So this basically uses a nuclear norm-based regularizer on the difference between the softmax values of clean and perturbed images. And this actually increases the diversity of attack, and also it improves the smoothness of the loss surface during training. So this was the best two-step defense, and we compare AJAT with this. So we get some gains in the on wide ResNet, and also in clean accuracy on ResNet 18. And now in the second half, in the second partition, we compare AJAT with some of the existing defenses, PGD adversarial training and trades. And we show three variants. One is using a single base augmentation and a single auto augment base transformation. And second is using 2 complex augmentations, and third is using 3 complex augmentations. And by increasing the number of complex augmentations, we actually observe improvements in the robust accuracy. But we find that the best trade-off between the performance and computational cost is basically by using 2 complex augmentations, where we are able to get compute which is similar to the trades AWP defense, and we are also able to get substantial gains in performance. So here on wide ResNet, we get gains of about 3% in clean accuracy and about 1%, less than 1% in robust accuracy. We also show improvements on CFAR 100 and ImageNet 10. So here on CFAR 100, we get significant gains of about, like if you compare this, the trades AWP defense, it gets clean accuracy of about 62, whereas the 2A method, it gets about 68. So there's a huge improvement in the clean accuracy and also an improvement in the robust accuracy. And similarly, even in the ImageNet 10, we get like large gains in clean and robust accuracy. And it's also worth noting that even the AJAT, the 2-step defense, that is also better than the trades AWP defense at a much lower computational cost. We next show the results of AJAT with higher attack steps and training epochs. So we use only 2 attack steps in our main training method, basically to make the computational cost similar to trades and to show that at a similar compute, we are able to get better results. But if we use higher attack steps and more training epochs, we actually get a further improvement in results. And here we increase the number of attack steps from 2 to 5 uniformly every 50 epochs. And we are able to do this because we have an increasing epsilon schedule. So when the perturbation bound is low, we don't need more than, we don't need too many attack steps. So that's the reason we also increase the attack steps during the training. And we again compare with the base trades AWP defense, and we get good gains in performance across both CFAR 10 and 100. We also show results on this common corruptions. And since we are able to use data augmentations effectively, so that's the reason why this accuracy also improves. Next, we show that AJAT can integrate with other augmentations as well, because the results that have been shown so far are with auto augment. And but we show several other augmentations like cutout, color, jitter, mix up, rand augment, augments, and cut mix. And we show that in all the cases, using the proposed approach of 1 base augmentations and 2 complex augmentations, we actually get gains in performance. And even in a case like cut mix, where just using cut mix actually degrades the performance significantly. But by using the proposed approach, we still get good gains when compared to the base results. We also show that the proposed method can scale to larger architectures. So if we move from WideResNet 3410 to WideResNet 3420, then the improvements in clean accuracy increase from 6 to 7%. And even in robust accuracy, the improvements increase from 1.7 to 2.7%. So basically, since we are using augmentations, so the method is able to get higher gains when the model capacity increases, because its capacity to minimize the error on this stronger augmentations also improves. Next, we show that AJAT can also be integrated with other adversarial training algorithms. So our main method integrates with AWP, but we show 2 other methods. One is our ECCV work, Oracle Aligned Adversarial Training, and another is the helper-based adversarial training. And across different data sets, CFAR 10 and CFAR 100, and across ResNet 18 and WideResNet, we show good improvements in performance by integrating with AJAT. Finally, we show the computational efficiency of AJAT and ACAT. So firstly, if we compare trades with ACAT, we note that the train time, it reduces by more than 50%. So, but whereas we still have improvements in both clean and robust accuracy for both WideResNet and ResNet 18. And using the proposed method AJAT, again, the computational cost is less than the trades, and we get like around 5% improvement in clean accuracy and also around 2% improvement in robust accuracy, and similar gains in with WideResNet as well. So since we are using, although we use 2 separate batch norm layers in the during training, for inference, we use only the batch norm layer corresponding to the simple augmentations. And this is done because the inference time distribution is assumed to be similar to the train distribution, which is going to be more similar to the simple augmentations than the complex one. So there is no increase in the number of parameters during inference or the inference, the number of flops during inference. And there is a very slight increase in the number of parameters during training because of the separate batch norm layers. So on CFAR 10 and 100, we get we have a good position on the low robust bench leaderboard currently amongst the defenses which do not use additional data during training. And in fact, on CFAR 100 leaderboard, we are better than one of the defenses, one of the ICLR 22 defenses, which also uses synthetic images during training. So probably because CFAR 100 has more number of classes and lesser number of images per class, so the impact of data augmentations on CFAR 100 seems to be higher. So I would like to thank my collaborators, Samyak Jain and my advisor, Professor Venkatesh Babu. Samyak is a master's student and he's currently also applying for PhD this fall in machine learning. And Professor Venkatesh Babu is a professor at the Indian Institute of Science. Yeah, thank you all for your attention, and I can take more questions now. Here is the link to our GitHub repo.
Thanks, Sravanti, for the amazing talk. Sorry, did I interrupt anyone for the question? All right, so I guess regarding the results, there's something I wanted to ask.
Sure.
And this is a question I think you must have gotten a lot, is that the approach seems to be quite agnostic to different adversarial training algorithms. For example, I think the DeepMind work earlier, like regarding data augmentation, it is something like this is tool that you have developed that can be integrated, for example, with most of the techniques on robust bench.
Right.
So what if what if I take I think the 100 million synthetic images or any of the approaches that get 63 to 66% accuracy on CFAR10 and just simply let it train. So two questions there. One is like out of curiosity, like what's your take? Like, do we get another 2-3% boost there, or would we see diminishing returns? Like, are these like tremendous stride in performance? Do they go down when we really hit the ceiling?
Okay, so firstly, we haven't really tried integrating this with additional data, but what I expect is that like when people have tried using generated data, like additional synthetic images, they have probably taken it to the limit of getting accuracy improvements. So probably the amount of synthetic data which is being used today is being used because adding more synthetic data probably does not help that much. So in that case, I guess there would be diminishing returns by using augmentations as well, because definitely synthetic data is going to be much more closer to the trained data distribution than random augmentations. But the point of using augmentations is just that it's much simpler to implement. You don't have to train a DDPM-based model or a GAN to generate this data. And also, probably it's not possible to generate a huge diverse data set for high resolution images. In that case, again, augmentations helps. So maybe if a small fraction of synthetic data is used and there is still some margin for improvement, then definitely by using data augmentations, it will improve. But whether the 66% can improve, I'm not sure. It might be diminishing returns.
I see. Yeah, thanks a lot. It does feel like, at least from a data science perspective, that we might be hitting the ceiling,
right,
in adversarial training. But yeah, hopefully there might be some work that can further, like, maybe take it beyond 70 and see for that.
Yeah, I guess looking at this in the context of transformers also would help a lot.
Yeah, maybe. Any other question? I guess if there are no other questions, maybe we can thank our speaker again for a very engaging and informative talk. The recording will be will be available. So if you miss something, you can always catch up. And
Thank you everyone for joining in, and thank you once again, Vikash and the organizers, for having me here.